compiler, assembler, and interpreter. In this video, we are going to see about compiler, assembler, and interpreter. Compiler. Compiler is a translator program that translates a program written in high-level language HLL, the source program, and translates it into an equivalent program in medium-level language MLL, the target program. As an important part of a compiler is error showing to the programmer. Executing a program written in HLL programming language is basically of two parts. The source program must first be compiled translated into an object program, that is OBJ. Then the results object program, that is OBJ, is loaded into a memory executed. Assembler. Programmers found it difficult to write or read programs in machine language. They begin to use mnemonic symbols for each machine instruction, which they would subsequently translate into machine language. Such a mnemonic machine language is now called an assembly language. Programs known as assembler were written to automate the translation of assembly language into machine language. The input to an assembler program is called source program. The output is the machine language translation, that is object program. Interpreter. An interpreter is a program that appears to execute a source program as if it were machine language. Interpreter accepts the input, then processes the input and produces the output for those given output. Languages such as BASIC, Snowball, and Lisp can be translated using interpreters. Java also uses interpreter. The process of interpretation can be carried out in following phases: lexical analysis, syntax analysis, semantic analysis, direct execution. Advantages. Modification of user program can be easily made and implemented as execution proceeds. User program. Debugging a program and finding errors is a simplified task for a program used for interpretation. The interpreter for the language makes it machine independent. Disadvantages. The execution of the program is slower. Memory consumption is more. Use of linker and loader. In this video, we are going to see about use of linker and loader. Loader or linker. A loader or linker or link editor is a translator that takes one or more object modules generated by a compiler and combine them into a single synonymously on Unix environments. This program is known as a linkage editor in IBM mainframe OS. However, in some operating systems, the same program handles both the task of object linking and physical loading of a program. Linking. This is a process where a linker takes several object files and libraries as input and produces one executable object file. It retrieves from the input files and combines them in the executable code, the code of all the procedures that are referenced, and resolves all external references to actual machine addresses. The libraries include language-specific libraries, operating system libraries, and user-defined libraries. Loading. This is a process where a loader loads an executable file into memory, initializes the registers, heap, data, etc., and starts the execution of the program. If we look at the design of all these translators, designing a preprocessor or assembler or loader or linker is simple. But among all, the most complex translator is the compiler. The design of the first Fortran compiler took 18 years. The complexity of the design of the compiler mainly depends on the source language. With modern compiler tools like YACC, that is yet another compiler, Lexical analyzer, and data flow engines, the design of a compiler is made easy. Various types of compiler. In this video, we are going to see about various types of compiler. In this, we will discuss various types of compilers. Incremental compiler, cross compiler, incremental compiler. Incremental compiler is a compiler which performs the recompilation of only modified source rather than compiling the whole source program. The basic features of incremental compiler are: it tracks the dependencies between output and the source program. It produces the same result as full recompile. It performs fewer tasks than the recompilation. The process of incremental compilation is effective for maintenance. Cross-compiler. Basically, there exist three types of languages. Source language, that is the application program. Target language, in which machine code is written. The implementation language, in which a compiler is written. There may be a case that all these three languages are different. In other words, there may be a compiler which runs on one machine and produces the target code for another machine. Such a compiler is called cross-compiler. Thus, by using cross-compilation technique, platform independency can be achieved. To represent cross-compiler, T diagram is drawn as follows. T diagram with S as source, T as target and I as implementation. Cross-compiler. For source language L, the target language N gets generated, which runs on machine M. Source program analysis. In this video, we are going to see about source program analysis. Analysis consists of three phases: linear or lexical analysis, syntax analysis, semantic analysis. Linear or lexical analysis. It is also called scanning. It is the process of reading the characters from left to right and grouping into tokens having a collective meaning. For example, in the assignment statement A is equal to B plus C into 2, the characters would be grouped into the following tokens. The identifier 1A. The assignment symbol is equal to the identifier 2B, the plus sign plus, the identifier 3C, the multiplication sign asterisk, the constant 2, syntax analysis. It is called parsing or hierarchical analysis. It involves grouping the tokens of the source program into grammatical phrases that are used by the compiler to synthesize output. A syntax tree is a tree generated as a result of syntax analysis in which the interior nodes are the operators and the exterior nodes are the operands. Semantic analysis. It checks the source programs for semantic errors and gathers type information for the subsequent code generation phase. It uses a syntax tree to identify the operators and operands of statements. An important component of semantic analysis is type checking. Here, the compiler checks that each operator has operands that are permitted by the source language specification. The phases of a compiler. In this video, we are going to see about the phases of a compiler. The compiler is designed into two parts. The first phase is the analysis phase, while the second phase is called synthesis. The main objective of the analysis phase is to break the source code into parts. It then arranges these pieces into a meaningful structure or grammar of the language. Lexical analysis, syntax analysis, and semantic analysis constitute the analysis phase. The synthesis phase is concerned with the generation of target language statement which has the same meaning as a source statement. Lexical analysis. Lexical analysis identifies the lexical unit in a source statement. Then it classifies the units into different lexical classes. Example, IDs, constants, keyword, etc., and enters them into different tables. Consider following code: I integer, a comma b real. A is equal to b plus I. The statement a b plus I is represented as a string of token. Syntax analysis. The syntax analyzer checks each line of the code and spots every tiny mistake that the programmer has committed while typing the code. Syntax analyzers process the string of token to determine statement class and also check whether given statement is syntax-wise valid or not. Semantic analysis. The letter identifies the sequence of actions necessary to implement the meaning of a source statement. The analysis ends when the tree has been completely processed. Intermediate representation. IR contains intermediate code and table. Symbol table. Intermediate code. T1 is equal to int2 real, that is ID1. T2 is equal to T1 plus B. A is equal to T2. Code optimization. As the name suggests, this phase aims at optimizing the target code. The code can be optimized in terms of time taken to execute, length of the code, memory utilized, or any other criteria. Code generation. Target code is generated at this phase using the intermediate representation of the source program. The machine instructions perform the same task as the intermediate code. Registers are allocated to variables in the program. This has to be done carefully so as to avoid any clashes or repeated assignments. The synthesis phase may desire to hold the value of I star and temp in machine registers and may generate the assembly code. Conversion R, A register, I, add R, A register, B, move M, A register, A. Symbol table. A symbol table is a data structure used by a language translator such as a compiler or interpreter for storing names encountered in the source program along with relevant attributes for those names. Information about following entities is stored in symbol table. Variable or identifier, procedure or function. Keyword that is stored before lexical analysis starts, constant. Class name, label name, structure and union name. Symbol table is used in different phases of compiler as listed below. Semantic analysis. Check correct semantic usage of language constructs. Code generation. All program variables and temporaries need to be allocated some memory locations. Error detection. Leave variables undefined. To reduce the total number of variables used in a program, we need to reuse the temporaries generated by the compiler. Grouping of phases. In this video, we are going to see about grouping of phases. Compiler can be grouped into front and back ends. Front end analysis, that is machine independent. These normally include lexical and syntactic analysis, the creation of the symbol table, semantic analysis, and the generation of intermediate code. It also includes error handling that goes along with each of these phases. Back-end synthesis, that is machine dependent. It includes code optimization phase and code generation along with the necessary error handling and symbol table operations. Compiler passes. A collection of phase is done only once, that is single pass, or multiple times, that is multi-pass. Single pass usually requires everything to be defined before being used in source program. Multi-pass compiler may have to keep entire program representation in memory. Several phases can be grouped into one single pass, and the activities of these phases are interleaved during the pass. For example, lexical analysis, syntax analysis, semantic analysis, and intermediate code generation might be grouped into one pass. Tools for implement various phases of compiler. In this video, we are going to see about tools for implement various phases of compiler. These are specialized tools that have been developed for helping implement various phases of a compiler. The following are the compiler construction tools: parser generators, scanner generator, syntax-directed translation, automatic code generators, data flow engines, parser generators. These produce syntax analyzers, normally from input that is based on a context-free grammar. Example: YACC, that is yet another compiler. Scanner generator. These generate lexical analyzers, normally from a specification based on regular expressions. The basic organization of lexical analyzers is based on finite automation. Syntax-directed translation. These produce routines that walk the parse tree and as a result generate intermediate code. Each translation is defined in terms of translations at its neighbor nodes in the tree. Automatic code generators. It takes a collection of rules to translate intermediate language into machine language. The rules must include sufficient details to handle different possible access methods for data. Data flow engines. It does code optimization using data flow analysis, that is, the gathering of information about how values are transmitted from one part of a program to each other part. The role of the lexical analyzer. In this video, we are going to see about the role of the lexical analyzer. Lexical analysis is the process of converting a sequence of characters into a sequence of tokens. A program or function which performs lexical analysis is called a lexical analyzer or scanner. A lexer often exists as a single function which is called by a parser or another function. The role of the lexical analyzer. The lexical analyzer is the first phase of a compiler. Its main task is to read the input characters and produce as output a sequence of tokens that the parser uses for syntax analysis. Upon receiving a getNext token command from the parser, the lexical analyzer reads input characters until it can identify the next token. Concept of input buffering. In this video, we are going to see about concept of input buffering. We often have to look one or more characters beyond the next lexeme before we can be sure we have the right lexeme. As characters are read from left to right, each character is stored in the buffer to form a meaningful token. We introduce a two-buffer scheme that handles large look-ahead safely. We then consider an improvement involving sentinels that saves time checking for the ends of buffers. Buffer pass. A buffer is divided into two n-character halves. Each buffer is of the same size n, and n is usually the number of characters on one disk block. Example, 1024 or 4096 bytes. Using one system read command, we can read n characters into a buffer. If fewer than n characters remain in the input file, then a special character represented by EOF marks the end of the source file. Two pointers to the input are maintained. Pointer lexeme beginning marks the beginning of the current lexeme, whose extent we are attempting to determine. Pointer forward scans ahead until a pattern match is found. Once the next lexeme is determined, forward is set to the character at its right end. The string of characters between the two pointers is the current lexeme. After the lexeme is recorded as an attribute value of a token returned to the parser, lexeme_beginning is set to the character immediately after the lexeme just found. Advancing forward pointer. Advancing forward pointer requires that we first test whether we have reached the end of one of the buffers, and if so, we must reload the other buffer from the input and move forward to the beginning of the newly loaded buffer. If the end of second buffer is reached, we must again reload the first buffer with input and the pointer wraps to the beginning of the buffer. Sentinels. For each character read, we make two tests. One for the end of the buffer, one to determine what character is read. Sentinel arrangement. Any EOF that appears other than at the end of a buffer means that the input is at an end. Token specification. In this video, we are going to see about token specification. There are three specifications of tokens: strings, language, regular expression. Strings and languages. An alphabet or character class is a finite set of symbols. A string over an alphabet is a finite sequence of symbols drawn from that alphabet. A language is any countable set of strings over some fixed alphabet. The length of a string S, usually written modulus S, is the number of occurrences of symbols in S. For example, banana is a string of length 6. The empty string, denoted epsilon, is the string of length 0. Operations on strings. The following string-related terms are commonly used. Prefix. A prefix of string S is any string obtained by removing 0 or more symbols from the end of string S. For example, ban is a prefix of banana. A suffix of string S is any string obtained by removing 0 or more symbols from the beginning of S. For example, nana is a suffix of banana. Substring. A substring of S is obtained by deleting any prefix and any suffix from S. For example, nan is a substring of banana. Subsequence. A subsequence of S is any string formed by deleting 0 or more, not necessarily consecutive positions of S. For example, ban is a subsequence of banana. Operations on languages. The following are the operations that can be applied to languages: union, concatenation, clean closure, positive closure. The following example shows the operations on strings. Let L is equal to 0, 1 and S is equal to A, B, C. Union. L union S is equal to 0, 1, A, B, C. Concatenation. L dot S is equal to 0A, 1A, 0B, 1B, 0C, 1C. Clean closure. L to the power of asterisk is equal to epsilon, 0, 1, 0, 0 going on. Positive closure. L to the power of plus is equal to 0, 1, 0, 0 goes on. Regular expressions. Each regular expression R denotes a language L of R. Here are the rules that define the regular expressions over some alphabet and the languages that those expressions denote. epsilon is a regular expression and L of epsilon is epsilon, that is, the language whose sole member is the empty string. If A is a symbol in, then A is a regular expression and L of A is equal to A, that is, the language with one string of length 1 with A in its one position. Suppose R and S are regular expressions denoting the languages L of R and L of S, then RS is a regular expression denoting the language L of R union L of S. RS is a regular expression denoting the language L of R L of S. R to the power of asterisk is a regular expression denoting L of R to the power of asterisk. R is a regular expression denoting L of R. The unary operator asterisk has highest precedence and is left associative. Concatenation has second highest precedence and is left associative. Slash has lowest precedence and is left associative. Regular set. A language that can be defined by a regular expression is called a regular set. If two regular expressions R and S denote the same regular set, we say they are equivalent and write R is equal to S. There are a number of algebraic laws for regular expressions that can be used to manipulate into equivalent forms. For instance, R slash S is equal to S slash R is commutative. R slash of S slash T is equal to R slash S into slash T is associative. Regular definitions. Giving names to regular expressions is referred to as a regular definition. If summation is an alphabet of basic symbols, then a regular definition is a sequence of definitions of the form D1 produce R1, D2 produce R2, up to Dn produce Rn. Each Di is a distinct name. Each Ri is a regular expression over the alphabet summation union of D1, D2 up to Di minus 1. Example, identifier is a set of strings of letters and digits beginning with a letter. Regular definition for this set. Letter provides A slash B slash up to Z slash, A slash B slash up to Z slash. Digit provide 0 slash 1 slash up to 9 slash. ID provides letter, that is, letter slash digit to the power of asterisk. Shorthands. Certain constructs occur so frequently in regular expressions that it is convenient to introduce notational shorthands for them. One or more instances, that is plus. The unary postfix operator plus means one or more instances of. If R is a regular expression that denotes the language L of R, then R to the power plus is a regular expression that denotes the language L of R to the power plus. Thus, the regular expression A to the power plus denotes the set of all strings of one or more A-S. The operator plus has the same precedence and associativity as the operator asterisk. 0 or 1 instance. The unary postfix operator means 0 or 1 instance of. The notation R is a shorthand for R slash epsilon. If R is a regular expression, then R is a regular expression that denotes the language. L of R union epsilon. Character classes. The notation of A, B, C, where A, B and C are alphabet symbols, denotes the regular expression A/B/C. Character class such as A-Z denotes the regular expression A/B/C/D/ up to Z/. We can describe identifiers as being strings generated by the regular expression A-ZA-Z into A-ZA-Z0 9 to the power of asterisk. Non-regular set. A language which cannot be described by any regular expression is a non-regular set. Example: the set of all strings of balanced parentheses and repeating strings cannot be described by a regular expression. This set can be specified by a context-free grammar. Overview of token recognition. In this video, we are going to see about overview of token recognition. Consider the following grammar fragment. Statement belongs if expression then statement, or if expression then statement else statement, or epsilon. Expression belongs to term reloop term, or term belongs id, or num, where the terminals if, then, else, reloop, id and number generate sets of strings. For this language fragment, the lexical analyzer will recognize the keywords if, then, else, as well as the lexeme denotes by reloop, id and number. To simplify matters, we assume keywords are reserved, that is, they cannot be used as identifiers. Transition diagrams. It is a diagrammatic representation to depict the action that will take place when a lexical analyzer is called by the parser to get the next token. It is used to keep track of information about the characters that are seen as the forward pointer scans the input. A language for specifying lexical analyzers. In this video, we are going to see about a language for specifying lexical analyzers. There is a wide range of tools for constructing lexical analyzers. Lex, YACC, Lex. Lex is a computer program that generates lexical analyzers. Lex is commonly used with the YACC parser generator. Creating a lexical analyzer. First, a specification of a lexical analyzer is prepared by creating a program lex.l in the Lex language. Then, lex.l is run through the Lex compiler to produce a C program lex.yy.c. Finally, lex.yy.c is run through the C compiler to produce an object program ma.out, which is the lexical analyzer that transforms an input stream into a sequence of tokens. Lex specification. A Lex program consists of three parts: definitions, rules, user subroutines. Definitions include declarations of variables, constants, and regular definitions. Rules are statements of the form P1 of action 1, P2 of action 2 up to Pn of action n, where Pi is regular expression and action I describes what action the lexical analyzer should take when pattern Pi matches a lexeme. Actions are written in C code. User subroutines are auxiliary procedures needed by the actions. These can be compiled separately and loaded with the lexical analyzer. YACC, yet another compiler. YACC provides a general tool for describing the input to a computer program. The YACC user specifies the structures of his input together with the code to be invoked as each such structure is recognized. Lexical Analyzer Generator Design. In this video, we are going to see about Lexical Analyzer Generator Design. We discussed two approaches based on NFAs and DFAs. The latter is essentially the implementation of Lex. The program that serves as a lexical analyzer includes a fixed program that simulates an automation. At this point, we leave open whether that automaton is deterministic or non-deterministic. The rest of the lexical analyzer consists of components that are created from the Lex program by Lex itself. A Lex program is turned into a transition table and actions, which are used by a finite automaton simulator. A transition table for automaton. Those functions that are passed directly through Lex to the output. The actions from the input program, which appear as fragments of code to be invoked at the appropriate time by the automaton simulator. To construct the automaton, we begin by taking each regular expression pattern in the Lex program and converting it to an NFA. We need a single automaton that will recognize lexemes matching any of the patterns in the program. So, we combine all the NFAs into one by introducing a new start state with epsilon transitions to each of the start states of the NFAs Ni for pattern Pi. Pattern matching based on NFAs. In this video, we are going to see about pattern matching based on NFAs. If the lexical analyzer simulates an NFA, then it must read input beginning at the point on its input, which we have referred to as lexeme begin. As it moves a pointer called forward ahead in the input, it calculates the set of states it is in at each point. Eventually, the NFA simulation reaches a point on the input where there are no next states. At that point, there is no hope that any longer prefix of the input would ever get the NFA to an accepting state. Rather, the set of states will always be empty. Thus, we are ready to decide on the longest prefix, that is a lexeme matching some pattern. We look backwards in the sequence of sets of states until we find a set that includes one or more accepting states. If there are several accepting states in that set, pick the one associated with the earliest pattern Pi in the list from the Lex program. Move the forward pointer back to the end of the lexeme and perform the action AI associated with pattern Pi. DFAs for lexical analyzers. Architecture resembling the output of Lex to convert the NFA for all the patterns into an equivalent DFA using the subset construction. Within each DFA state, if there are one or more accepting NFA states, determine the first pattern whose accepting state is represented and make that pattern the output of the DFA state. Implementing the look-ahead operator. The Lex look-ahead operator / in a Lex pattern R1 by R2 is sometimes necessary because the pattern R1 for a particular token may need to describe some trailing context R2 in order to correctly identify the actual lexeme. When converting the pattern R1 by R2 to an NFA, we treat the / as if it were epsilon, so we do not actually look for a / on the input. Rather, the end occurs when the NFA enters a state S such that S has an epsilon transition on the that is imaginary /. There is a path from the start state of the NFA to state S that spells out X. There is a path from state S to the accepting state that spells out Y. X is as long as possible for any XY satisfying conditions 1 to 3. If there is only one epsilon transition state on the imaginary / in the NFA, the end of the lexeme occurs when this state is entered for the last time, as the following example. If the NFA has more than one epsilon transition state on the imaginary /, then the general problem of finding the correct state S is much more difficult. Algorithm for optimized pattern matchers. In this video, we are going to see about algorithm for optimized pattern matchers. In this section, we present 3 algorithms that have been used to implement and optimize pattern matchers constructed from regular expressions. The first algorithm is useful in a Lex compiler because it constructs a DFA directly from a regular expression without constructing an intermediate NFA. The resulting DFA also may have fewer states than the DFA constructed via an NFA. The second algorithm minimizes the number of states of any DFA by combining states that have the same future behavior. The algorithm itself is quite efficient, running in time O of n log n, where n is the number of states of the DFA. The third algorithm produces more compact representations of transition tables than the standard two-dimensional table. Important states of an NFA. We call a state of an NFA important if it has a non-epsilon out transition. Notice that the subset construction uses only the important states in a set T when it computes epsilon closure, move of T, A, the set of states reachable from T on input A. That is, the set of states moves S, A is non-empty only if states is important. During the subset construction, two sets of NFA states can be identified, that is treated as if they were the same set if they have the same important states and either both have accepting states or neither does. When the NFA is constructed from a regular expression by algorithm, we can say more about the important states. The only important states are those introduced as initial states in the basis part for a particular symbol position in the regular expression. That is, each important state corresponds to a particular operand in the regular expression. The constructed NFA has only one accepting state, but this state, having no out transitions, is not an important state. By concatenating unique right-end marker hash to a regular expression R, we give the accepting state for R a transition on hash, making it an important state of the NFA for R hash. In other words, by using the augmented regular expression R hash, we can forget about accepting states as the subset construction proceeds. When the construction is complete, any state with a transition on hash must be an accepting state. The important states of the NFA correspond directly to the positions in the regular expression that hold symbols of the alphabet. An interior node is called a cat node or star node if it is labeled by the concatenation operator, that is dot, union operator, slash, or star operator, asterisk, respectively. We can construct a syntax tree for a regular expression just as we did for arithmetic expressions. Functions computed from the syntax tree. To construct a DFA directly from a regular expression, we construct its syntax tree and then compute for functions nullable, first pause, last pause, and follow pause, defined as follows. Each definition refers to the syntax tree for particular augmented regular expression R hash. Nullable of n is true for a syntax tree node n if and only if the sub-expression represented by n has epsilon in its language. That is, the sub-expression can be made null or the empty string, even though there may be other strings it can represent as well. First pos of n is a set of positions in the subtree rooted at n that correspond to the first symbol of at least one string in the language of the sub-expression rooted at n. Last pos of n is a set of positions in the subtree rooted at n that correspond to the last symbol of at least one string in the language of the sub-expression rooted at n. Follow pos of p for a position p is a set of positions q in the entire syntax tree such that there is some string x is equal to a1, a2 up to an in L of R hash, such that for some I, there is a way to explain the membership of x in L of R hash by matching ai to position p of the syntax tree and ai plus t to position q. Computing nullable, first pos and last pos. We can compute nullable, first pos and last pos by a straightforward recursion on the height of the tree. The rules for last pos are essentially the same as for first pos, but the roles of children C1 and C2 must be swapped in the rule for a cat node. Computing follow pos. There are only two ways that a position of a regular expression can be made to follow another. If n is a cat node with left child C1 and right child C2, then for every position I in last pos, that is C1, all positions in first pos, that is C2, are in follow pos of I. If n is a star node and I is a position in last pos of n, then all positions in first pos of n are in follow pos of I. Converting a regular expression directly to a DFA. Algorithm 1. Construction of a DFA from a regular expression R. Input a regular expression R. Output a DFA D that recognizes L of R. Method. Construct a syntax tree T from the augmented regular expression R hash. Compute nullable, first pos, last pos, and follow pos for T using the methods. Construct D states, the set of states of DFA D and DTran, a transition function for D, by the procedure. The states of dash sets of positions in T. Initially, each state is unmarked and a state becomes marked just before we consider its out transitions. The start state of D is first pos, that is N0, where node number is the root of T. The accepting states are those containing the position for the end marker symbol hash. Minimizing the number of states of a DFA. For instance, note that the DFAs of both recognize language L of a/b.abb. Not only do these automata have states with different names, but they don't even have the same number of states. If we implement a lexical analyzer as a DFA, we would generally prefix a DFA with as few states as possible, since each state requires entries in the table that describes the lexical analyzer. The matter of the names of states is minor. States A and C are actually equivalent in the sense that neither is an accepting state, and on any input they transfer to the same state to B on input A and to C on input B. Likewise, state B behaves like state 1, 2, 3, 4, state D behaves like state 1, 2, 3, 5, and state E behaves like state 1, 2, 3, 6. It turns out that there is always a unique, that is, up to state names, minimum state DFA for any regular language. Moreover, this minimum state DFA can be constructed from any DFA for the same language by grouping sets of equivalent states. In the case of L of A/B to the power of asterisk ABB, the minimum state DFA, and it can be constructed by partitioning the states as A, C, B, D, E. We say that string X distinguishes state S from state T if exactly one of the states reached from S and T by following the path with label X is an accepting state. State S is distinguishable from state T if there is some string that distinguishes them. Trading time for space in DFA simulation. In this video, we are going to see about trading time for space in DFA simulation. The simplest and fastest way to represent the transition function of a DFA is a two-dimensional table indexed by states and characters. Given a state and next input character, we access the array to find the next state and any special action we must take. Example: returning a token to the parser. Since a typical lexical analyzer has several hundred states in its DFA and involves the ASCII alphabet of 128 input characters, the array consumes less than a megabyte. However, compilers are also appearing in very small devices where even a megabyte of storage may be too much. For such situations, there are many methods that can be used to compact the transition table. For instance, we can represent each state by a list of transitions, that is, character state pairs ended by a default state that is to be chosen for any input character not on the list. If we chose as the default the most frequently occurring next state, we can often reduce the amount of storage needed by a large factor. We may think of this structure as 4 arrays as suggested. The base array is used to determine the base location of the entries for state S, which are located in the next and check arrays. The default array is used to determine an alternative base location if the check array tells us the one given by base of S is invalid. To compute next state of S, A, the transition for state S on input A we examine the next and check entries in location L is equal to base of S plus A, where character A is treated as an integer, presumably in the range 0 to 127. If check of L is equal to S, then this entry is valid and the next state for state S on input A is next of L. If check of L not equal to S, then we determine another state T is equal to default of S and repeat the process as if T were the current state. More formally, the function next state is defined as follows: int next state of S, A. If of check of base of S plus A is equal to S, return next of base of S plus A. Else return next state of default of SA. The intended use of structure is to make the next check array short by taking advantage of the similarities among states. For instance, state T, the default for state S, might be the state that says we are working on an identifier like state 10. On input character E, we must go from state S to a special state that remembers that we have seen the but otherwise state S behaves as T does. While we may not be able to choose base values so that no next check entries remain unused, experience has shown that the simple strategy of assigning base values to states in turn and assigning each base of S value the lowest integer so that the special entries for state S are not previously occupied utilizes little more space than the minimum possible.